A single particle could rewrite the laws of the universe. That's the strange matter hypothesis. It's a theory in physics. It says everything around you, the ground, the stars, all of it might be fundamentally unstable. We're going to look at the science, a potential cosmic chain reaction, what that means for our place in reality. We'll go into the cores of dead stars. Crushing places, that's where this strange substance could be born. And we'll look at whether our entire cosmos is transforming, silently, into something alien. To live on the edge of a discovery like that, what does that feel like? Atoms are the building blocks of everything we know. You, me, the planet, the sun. And inside every atom you have a nucleus, protons and neutrons. For a long time we thought those were the smallest things, but they're not. Protons and neutrons are made of quarks. Up quarks and down quarks. That's ordinary matter. It's the stable state for our world. But there's a theory. Under immense pressure, like inside a neutron star, that stability might break down. Protons and neutrons could melt. Their boundaries dissolve, and all those up and down quarks could mix with a third type strange quarks. They'd merge into one continuous substance. A quark soup, strange matter, and the idea is, this soup might be more stable than the atoms we're made of. It could be the true ground state of the universe. Which means everything we see, everything we are, is in a higher energy state. Like a ball balanced on a hilltop. So then the question becomes, where in the universe could this actually happen? Deep inside a collapsed star, reality gets squeezed into something new. You take the entire mass of a mountain, all that rock and earth, and you crush it down to fit inside a single sugar cube. That's the core of a neutron star. It's a place of impossible density. A single teaspoonful would weigh billions of tons. That weight would punch a hole straight through our planet. This isn't just a different environment. It's a different state of existence. A celestial pressure cooker where the rules we know start to bend and break. These stellar remnants are the universe's ultimate laboratories. They're the only natural places we know where the pressure is that immense, the gravity that crushing. It might trigger a fundamental change in matter itself, which brings us to the Bodmer-Witten Hypothesis. It's a compelling idea. It suggests that under these insane conditions, something remarkable happens. The neutrons, which are normally stable particles, might find it energetically favorable to just dissolve. Their structure melts away. The quarks inside them are set free. They mingle with a new, stranger type of quark. They form that continuous, ultra-dense soup we call strange matter. So in this view, the heart of a neutron star isn't just a dense object. It's a potential factory, a crucible where the universe might be forging a more stable form of reality. The pressure acts like a key. It unlocks a door to a state that could be the true, lowest energy configuration for all matter. But this leads to a profound question, an unsettling one. What if this substance, once created, doesn't stay locked away? What if a piece of it gets chipped off? In a stellar collision or some violent event, and it escapes its unimaginably dense prison. It enters the wider cosmos. The implications of that possibility are where the hypothesis changes. It transforms from a curious idea into a potential cosmic narrative. That stable, alien substance, if it exists, might not stay inside those stars, it could get out. In the chaos of a neutron star collision or some other cataclysm, a tiny piece could break free. Physicists call these fragments stranglets. They're like microscopic nuggets. A stranglet could be smaller than an atom, but unimaginably heavy. And it could be perfectly stable, just floating alone in space. Think of it like a seed crystal. You have a supersaturated solution, it's liquid, until you drop in that one tiny seed. Then the whole thing crystallizes. It turns solid because that seed gave it a template. A starting point. The strange matter idea suggests our universe might be like that. All the ordinary matter around us, the atoms in your hand, in the air, in the planets, might be like that solution. It's stable for now, but it's not the most stable state possible. It's waiting, and a Strangelet would be that seed. If one of these specks drifted into contact with an ordinary atomic nucleus, something simple could happen. The Strangelet might not just sit there. It could absorb the nucleus. The protons and neutrons would dissolve, their quarks assimilated into the strange matter. That conversion would release a burst of energy, and the Strangelet would grow slightly larger. Now it has more mass, a greater surface area. It could then convert the next atom it touches even faster. That's the heart of the conversion idea. A domino effect at the most fundamental level. One atom triggers the next, and the next, in a chain reaction that could, in theory, spread without limit. The scale of this is what's hard to grasp. It starts with a single, invisible particle, smaller than anything we can see. And it ends with the potential transformation of a planet, a star, a galaxy. From a single seed, a new state of reality could grow, converting everything in its path into a dense, cold sea of strange quark matter. The universe as we know it would be rewritten, not with a bang, but with a silent, physical change. The conversion would be a silent reordering. The most basic architecture of the universe changes. To understand it, you look at the glue, the strong nuclear force. It's what holds quarks together inside protons and neutrons. In our world, it creates a stable arrangement, but it's a tense one. The strange matter idea says there's a more efficient way. Think of a pile of magnets, all repelling and attracting, a jumbled structure. That's ordinary matter. Now imagine snapping them into a perfect grid. All that tension gets released. The grid is solid, it's stable. It can't go back to being a messy pile. That's the proposed state. Strange matter. The strong force finds a new way to organize. A lower energy way, especially when you add strange quarks. This isn't a chemical reaction. It's not an explosion, it's a phase transition, like water turning to ice. The molecules are the same, but they lock into a more orderly structure. In this version, the fundamental particles rearrange. The quarks become a denser, more stable soup. It releases energy, but not a flash, more like a wave of crystallization, moving through the fabric of a material, and that's where it becomes cosmic. Once a seed of strange matter starts to grow, it establishes a conversion front, a boundary between the old universe and the new. At that front, any atomic nucleus it touches gets dismantled. Its quarks are assimilated. The energy from that conversion then fuels the conversion of the next layer of atoms. The front propagates, not slowly, at a significant fraction of the speed of light. From a human perspective, it's instantaneous. A planet, from the point of first contact, would be transformed in a flash. Its mountains, its oceans, the atmosphere. All of it ceases to exist, replaced by a hyper-dense sphere, featureless strange quark matter. A star would suffer the same fate. Its nuclear fires snuffed out as its fuel changed state. The front would move from star to star, galaxy to galaxy, leaving behind a cold, dark, dense new universe. This isn't destruction in the classic sense. It's a rewriting of the rules, and it compels a question. If this is a possible outcome, a more stable state for all matter, then why hasn't it happened yet? Or maybe, more unsettlingly, how do we know it hasn't already begun? This is the ultimate cosmic detective story. How would we know if this has already happened? If a conversion front moved through a galaxy a billion years ago, what would be left for us to see? The answer is simple and profound. We might see nothing. A galaxy turned entirely to strange matter would be dark, dense and cold. Its stars wouldn't shine, it would be a ghost, a shadow in the cosmos, visible only by how it pulls on the light from things behind it. Astronomers have found objects that don't fit. Some neutron stars seem too small or too massive for our models of ordinary matter. Could those be strange stars? Not neutron stars at all, but a single, continuous blob of that stable quark matter. Their existence would be a clue that the transformation isn't just possible. It's real, somewhere. The search isn't only out there. It's happening here, on Earth, in tunnels deep underground, at places like the Large Hadron Collider. Scientists are trying to recreate the early universe in a controlled way. They smash particles together at nearly light speed, creating moments of incredible energy and density. Microscopic fireballs. For a fraction of a second, matter might exist in a state not seen since the Big Bang. They sift through the debris of these collisions, looking for any anomalous signature, a particle that's too heavy, too stable, or behaves in a way that defies the standard model. They are hunting for a strangelet. The fact we haven't found one is a crucial piece of data. It places limits on how easily this substance can be created. It suggests that if strange matter exists, it needs conditions more extreme than our most powerful machines can make. This search is about more than a new particle. It's an attempt to answer a foundational question about the fabric of reality. Are we living in the universe's most stable, final form? Or are we just a temporary arrangement, a higher energy state, waiting for a trigger to find its true and terrifyingly different equilibrium? The search for strange matter touches on a deeper fear in physics. It's this idea that the universe might be resting on unstable ground. That concept is called vacuum metastability, or vacuum decay. It's a parallel kind of cosmic nightmare. And both ideas share a core principle: that our reality, the laws of physics as we know them, might not be in their final, most stable form. We could be living in a temporary state, a bubble of higher energy, and somewhere out there, a lower, more stable state is waiting. If our bubble pops, everything changes. Imagine a mountain range. Our universe is in a lush, green valley. It seems stable. We have stars, planets, atoms, but this valley isn't at the lowest possible point. It's just a dip on a mountainside. Far below, hidden by clouds, there's a deeper chasm, a true bottom. That's the true vacuum state. Now, the strange matter hypothesis is like finding a crack in the floor of our valley. A specific, physical pathway where matter itself can start rolling downhill toward that deeper state. A strangelet is a pebble that starts the landslide. Vacuum decay is different. It's the valley itself collapsing. In quantum field theory, the vacuum isn't empty. It's a seething sea of potential. The properties of particles, the strength of forces, all come from this underlying field. Our valley represents one configuration of that field. But if a quantum fluctuation, a random burp in space-time, creates a tiny bubble of the true vacuum, that bubble would expand. At the speed of light, the moment its wall touches you, the rules rewrite. The constants of nature change, atoms could no longer form. The fundamental forces like electromagnetism might cease to exist. Everything we recognize as reality would simply stop being possible. It would be an end, not with fire or ice, but with a silent reconfiguration of the code of the cosmos. The comparison is chilling. One threat converts matter, the other erases the very laws that allow matter to exist. Yet they are kin. They tell us our cosmic footing might be more fragile than we ever dared believe. We are balancing on a slope, not standing on solid ground. This realization forces a shift. It moves the discussion from a specific astronomical curiosity to a broader philosophical question. What does it mean to live in a universe that might be fundamentally transient? The possibility itself has a certain weight. It's not just about physics. It touches something human. That drive to understand, to push into the unknown. It's always had a shadow, a question of responsibility. What if the search, the experiment itself, could set off the very thing we're trying to study? This isn't fiction. It's a real debate that's happened. The idea is, in a particle accelerator under extreme conditions, we might theoretically create something called a strangelet. The chance is incredibly small. Most physicists see it as negligible, but the consequence, however remote, is total. It brings up the precautionary principle. If an action carries a suspected risk of severe harm, you proceed with caution, even without full proof. Here, the suspected risk is the end of everything. So where does that leave the pursuit? Do we stop building more powerful machines? Halt experiments over a theoretical, nearly impossible outcome? It's playing with cosmic fire. The burden is heavy. You have to weigh the value of knowledge, of understanding reality itself, against a risk that's almost zero, but whose impact is infinite. Some say certain doors are better left closed, that some knowledge has a price too high. Others argue that not seeking understanding is the greater risk. That hiding from the truth leaves us vulnerable to forces we won't comprehend. This tension is at the heart of all exploration. The first sailors leaving shore felt it. The astronauts looking back at Earth. Every step into the unknown carries a potential cost. The strange matter idea makes that cost stark, terrifyingly clear. It turns the physicist from an observer into a potential actor in a cosmic story. And it asks a reflective question. In trying to read the universe's deepest code, do we accept that we might one day, accidentally, press a key that rewrites everything? Most physicists don't actually buy the doomsday scenario. They have a counter-argument. It comes from the same physics that makes strange matter interesting. It's called the Nucleation Barrier. That might be why the universe is safe from this kind of chain reaction. Think about supercooled water. You can cool it below freezing and it stays liquid. It's unstable. It's waiting for a trigger. That trigger is a seed crystal, a tiny speck of ice. Drop it in and the water freezes instantly. It solidifies from that point outward. The strange matter idea says our universe is like that. Ordinary matter is the supercooled water. A seed of strange matter could start the conversion. But here's the thing. Creating that first seed from scratch is incredibly hard. With the water, the molecules have to spontaneously arrange into a perfect ice pattern. That initial formation needs a huge input of energy. There's a barrier to overcome. It's far easier for the seed to come from outside, from an existing piece of ice. The nucleation barrier for strange matter is the same idea, but cosmic. To create a stable, dangerous strangelet from ordinary particles, you'd have to overcome an immense energy hurdle. You'd need to pack a vast number of strange quarks together in just the right configuration, all at once, against forces trying to pull it apart. It's not impossible. But the conditions are so specific, so finely tuned. Many researchers argue the probability is vanishingly small. They point out something else. For a strangelet to be a danger, it likely needs a specific property. A negative charge. A positively charged one would be repelled by atomic nuclei. It would never get close enough to start a chain reaction. But creating a negatively charged, stable strangelet requires a perfect recipe of quarks. A very unlikely one. The argument goes that if it were easy, the universe would have already done it. The fact we exist, that galaxies shine with ordinary stars, is evidence. This nucleation barrier is real, and it's very high. It acts as a cosmic safety catch, so the theoretical pathway exists. But the first step may be so improbable the chain reaction never begins. This perspective doesn't dismiss strange matter. It fences it in. It suggests that if strange stars exist, they are sealed tombs. Their contents might be permanently locked away by the very physics that created them. The seed might never escape the crushing pressure of its birthplace. It introduces a balance, a scientific skepticism. It tempers the more extreme narratives. Between a fascinating hypothesis and a cosmic catastrophe, there often stands a very large wall. A wall of very difficult physics. Our own survival is a clue. The universe has been running experiments for billions of years, far more violent than anything we could build. Ultra-high-energy cosmic rays, particles from black holes and exploding stars, moving almost at light speed. They've slammed into everything, planets, moons, and especially those dense neutron stars. If a neutron star collision or one of those impacts could easily create a dangerous strangelet, it probably would have happened by now. Across that much time, across countless galaxies, the improbable starts to feel almost inevitable, but we're still here. Our galaxy still shines with ordinary stars. Which suggests it hasn't happened. That's a profound point. It's called the Anthropic Argument. In simple terms, if the universe were prone to that kind of chain reaction, observers like us probably wouldn't exist to ask the question. Our presence is itself a data point. It hints that the rules, the parameters of physics, might be tuned to make that specific catastrophe extraordinarily rare. Or maybe impossible. It doesn't disprove strange matter, but it argues against it being an imminent, lurking danger. The cosmos has been stress-testing its own stability for eons. And so far, it's passed. That shifts the perspective, from a doomsday scenario to a fascinating physical possibility. One that's likely contained. The search continues. Not from fear, but from a desire to map what's real. Physics could have built the firewall. The runaway conversion idea is terrifying in its simplicity. But the reality of quarks and forces is more intricate. Two subtle properties might act as safeguards: electric charge and surface tension, like a combination to a cosmic lock. For a strangelet to be dangerous, to start that chain reaction, it likely needs both the right size and the right electrical signature. Start with charge. An atomic nucleus is positively charged, packed with protons. If a strangelet also had a positive charge, they'd repel, like pushing the same ends of two magnets together. They'd never touch. A neutral strangelet with no net charge might just drift through matter, but a slightly negative charge, that's different. It would be attracted to the positive nucleus. It could make contact, and that contact is where the conversion could begin. So the fate of the universe, in this idea, hinges on the net charge of a microscopic speck. The calculations get interesting here. When physicists model strange matter formation in extreme environments, the numbers often point away from danger. The dynamics of quark-gluon plasmas, that soupy state in neutron stars or collisions, tend to favor strangelets that are positively charged or neutral. They'd be stable. They might even exist out there, but they'd be inert, cosmically sterile, unable to start a chain reaction because they can't get close enough to ordinary matter. Then there's surface tension, not the surface tension of water on a leaf, a quantum effect on the scale of a femtometer. In a droplet of strange matter, the quarks at the surface experience different forces than the core. This creates a kind of skin, a tension that holds the droplet together. If the droplet is too small, this surface tension can overwhelm it. It becomes energetically unfavorable to even exist. It would rather fall apart into individual neutrons. There's a minimum size, a critical mass, below which a stable strangelet cannot form. So even if a negative charge was created, it might need to be born already above a certain threshold to survive long enough to be a threat. This isn't a guarantee, but another filter. Another hurdle in a series of improbable steps. Together, these aren't dramatic barriers. They're quiet, technical details in the equations. A slight preference in charge here. A balance of forces there. They could be the universe's own subtle safety mechanisms woven into quantum reality. It suggests that if strange matter is real, it may be a contained wonder. A state of being the cosmos allows, but also carefully quarantines through the fine print of physical law. Strange matter started in physics journals. It was a theoretical idea. Then it moved into stories, into books and movies. It became this doomsday substance. A single drop that could eat a planet. In games, it's a glowing material. It powers alien machines. It corrupts worlds. These stories don't get into the technical details. They don't talk about nucleation barriers. They take the basic concept, this unstoppable conversion, and they just go with it. They make a hypothesis into a plot. And it works because it connects to something deep. This isn't a monster. It's not an army. It's a change to the rules. An invisible infection that rewrites reality from the inside. It plays on a fear of forces we can't see, forces we can't reason with, forces we can't control. The threat is total, it's clean, it's impersonal, the end of the world but as a physics equation. These portrayals show a gap between the dramatic story and the careful language of real science. In a story, the strangelet is always the trigger. The chain reaction is a sure thing. It gives you a clear, visual ending, but science lives in the world of could and might, and under these very specific conditions, its climax is a paper full of math. Not a flash of light wiping out a galaxy. That contrast tells us something about how we think about risk and wonder. Our brains want stories, a compelling narrative about a universe-ending substance, no matter how unlikely, will always feel heavier than a dry statistic. It feels more real. This is how science feeds imagination. It gives a seed of real possibility, and storytellers let it grow into forests of what-if. The strange matter hypothesis was that seed. A scientific maybe that was just solid enough to build a nightmare on. So when we watch these stories, we're not just being entertained. We're running a kind of cultural experiment. We're asking, through the safety of fiction, what we would do if the rules were really that fragile. It turns abstract physics into something shared. It resonates because it speaks to an anxiety that the ground under our feet and the stars above might be less solid than they seem. The whole idea starts with quantum chromodynamics. That's the theory for the strong force, what holds nuclei together. It's the rulebook for quarks. At high energies in particle colliders, it works perfectly. The math is clean, but inside a neutron star, that's a different environment. It's dense, it's cold, it's low energy. The theory becomes difficult. It goes into what's called the non-perturbative regime. Our usual calculations break down. They don't converge. It's like knowing the physics of a water molecule, but trying to predict the shape of a snowflake. The rules are the same, but the complexity makes it impossible to calculate from scratch. That's the challenge. We have the fundamental theory, but applying it to these extreme places pushes it to the limit. And that gap, that's where the mystery is. So we have to rely on something else: models, educated guesses about matter when it's crushed beyond anything. That's the equation of state for ultra-dense matter. It's a relationship. How pressure changes with density under those conditions. Like a recipe for the most extreme material. You add mass to a neutron star, what happens? Does it shrink a little or a lot? Does the core stay as neutrons or become something new? The equation of state is the answer. And we don't know the right one. It's a major open question. Observations from gravitational waves from mergers, they give us clues, but they haven't given us a single answer. The strange matter idea is just one possible solution to that equation. One possible shape the recipe could take. It fits within quantum chromodynamics, even if we can't prove it from the theory alone. It sits in that gray area, a consequence of our incomplete map. This cosmic puzzle has several possible pieces, and strange matter is one of them. This uncertainty, it's not a failure. It's the frontier. It means we're still asking the questions, still probing the edges of what the forces allow. The universe keeps its deepest secrets under pressures we can't comprehend. Our theories are just the lanterns we're using to look into that dark. The inside of a neutron star. It might not be a simple, dense soup. It could be more like a cosmic lasagna. Layers of exotic states stacked on top of each other. And beyond strange matter, there's another possibility. It pushes the boundaries of weirdness even further. It's called color superconductivity. To get it, you look at a regular superconductor here on Earth. Electrons pair up. They overcome their natural repulsion. They move together without any resistance. That's a frictionless flow of electricity. A quantum mechanical dance. Now, inside a neutron star, the quarks themselves might do something similar. The strong force, the color force, could cause quarks to pair up. They wouldn't be moving electricity, they'd be moving color charge. That creates a color superconductor. A state where quarks flow without any resistance to the strong force. A bizarre kind of perfection, locked under that pressure. This isn't just a different flavor of quark soup. It's a fundamentally new organization of matter, and it gets stranger. Depending on temperature and density, different types of quark pairing might occur. Some theorists propose phases with poetic names. The color flavor locked phase, where quarks of different types and colors all lock into a coordinated pattern. Others imagine crystalline superconductors, where the quark pairs arrange themselves in a rigid lattice. The point is, the core might not be a uniform blob. It could be a dynamic, layered structure, a shell of ordinary neutrons, then a layer of free quarks, then a deeper region of color superconducting matter. And somewhere within that, pockets of strange matter might form. This complexity changes the game for our doomsday scenario. Creating a stable, dangerous strangelet isn't just about having enough pressure. It's about navigating this intricate quantum landscape. A seed of strange matter would have to form in just the right layer, with just the right conditions, and then survive a journey through other exotic phases to possibly escape. It's like trying to grow a perfect ice crystal in the middle of a turbulent, boiling pot of different liquids. The process becomes highly non-trivial. It depends on a precise and fragile cocktail: density, temperature, quantum stability. So when we picture that runaway conversion, we can't just imagine a simple seed dropping into water. We have to picture that seed trying to form and grow in a churning, multi-layered quantum forge. The very exoticness that makes these states possible might also act as a series of internal baffles, containing the most extreme possibilities within the star's heart. This layered view doesn't eliminate the strange matter hypothesis, but it embeds it within a richer, more chaotic reality. It suggests that if a dangerous strangelet is to be born, the universe must not only crush matter, it must also arrange it with a kind of flawless, cosmic precision. The universe runs its own experiments, and we're learning to read the results. So, how do you spot a star made of strange matter? It's in the subtle differences. Like finding a twin with a slightly different heartbeat. The first clue is size. For a neutron star, adding mass makes it smaller. Gravity gets stronger, squeezes it tighter. But for a strange star, the rules change. Adding mass might make it larger, or it could follow a completely different curve. That mass-radius relationship is a cosmic fingerprint. By measuring both the weight and the width of these objects, astronomers can check which model fits. It's like trying to guess what a dense ball is made of, just by seeing how heavy it is for its size. Some stars we've seen seem too small to be neutrons alone. They could be strange stars, or they could be telling us something else entirely. Then there's how they cool. A newborn neutron star is unbelievably hot. It cools by emitting neutrinos, ghostly particles that stream out, carrying energy away. The exact pattern of that cooling depends on what's inside. If the core is a soup of free quarks, the neutrino emission could be faster, or follow a different rhythm, than if it's a solid lattice of neutrons. By watching the temperature drop of young stellar remnants over years, over decades, you get a thermal image of their hearts. A strange star might cool in a way our models for ordinary neutron stars can't explain. Finally, consider the surface. A neutron star is thought to have a solid crust. A crystalline shell miles thick, harder than diamond. This crust can crack and shift, causing a starquake. When that happens, the star's spin changes abruptly. We see this as a glitch in the perfect radio tick of a pulsar. But a strange star might have no such solid crust. Its surface would be a smooth boundary between the vacuum of space and a sea of quark matter. Without a crust to fracture, its spin would be incredibly steady. Any glitches would have to come from a different mechanism. Perhaps from the fluid dynamics inside. So a pulsar with an unusually smooth rotation could be a candidate, a silent hint of a fundamentally different interior. This is where telescopes become our translators. Radio telescopes catch the precise pulses. X-ray observatories measure surface temperature, map hotspots. By combining data across the spectrum, we turn these distant objects into natural laboratories. Each observation is a test of fundamental physics, conducted on a scale we could never replicate. We're not just cataloging stars. We're probing the possible states of existence, using the cosmos itself as our guide. We aren't just watching the cosmos. We've built our own machines, our own crucibles to test these extreme states. The relativistic heavy ion collider, the Large Hadron Collider. They're our attempt to make a tiny piece of the early universe, or the core of a dead star, right here. They don't create sustained pressure. They create heat, unimaginable heat. In these circular tunnels, scientists accelerate heavy ions gold lead to over 99.999% light speed. Two beams, opposite directions, slammed together. The collision is cataclysmic. For a trillionth of a second, the temperature hits trillions of degrees. The protons and neutrons in those nuclei are obliterated. They melt, and for that instant, the quarks and gluons inside are set free. They form a droplet. Quark-gluon plasma. A primordial soup not seen since the first microseconds after the Big Bang. A fireball of creation. A glimpse into a state where the rules are simpler and everything is fluid. But this fireball is hot. It's expanding. It's the opposite of the cold, crushing, sustained pressure inside a neutron star. It's a violent flash, not a steady squeeze. The plasma exists for less than an eye blink before it cools and condenses back into a shower of ordinary particles. That distinction matters for the strange matter question. Could such a collision, by some freak accident, forge a stable Stranglet? The idea prompted serious safety reviews. Before the Large Hadron Collider reached full power, committees of independent physicists were tasked with investigating every conceivable risk. They examined cosmic ray data. They ran the numbers, they modeled the collisions. Their conclusion was unanimous. The risk of creating a stable, dangerous Stranglet in these experiments is vanishingly small. The environment is all wrong. Too hot, too chaotic, too brief. A stable Stranglet, if it can form at all, needs a very specific set of conditions. A cold, dense, quiet place where quarks can slowly find their most stable arrangement. A collision in a particle accelerator is a tornado. A neutron star core is a deep, still ocean trench. The tornado might contain the same water molecules, but it will never form a perfect ice crystal. And the safety reports noted something else. The universe has been running similar, and far more energetic, experiments for eons. Ultra-high-energy cosmic rays particles with millions of times more energy than our colliders can produce have been bombarding the Moon, and neutron stars for billions of years. If such collisions could trigger a catastrophic phase change, it would have happened already. The fact that we, and the galaxy around us, still exist is a powerful testament to the inherent stability of our vacuum, to the extraordinary improbability of that specific chain of events. Our machines let us touch the edge of the impossible. But they also confirm the robust, resilient nature of the reality we inhabit. This idea pushes things to the absolute limit. What if the universe is built to do this? Not as a mistake, but as a feature. In that view, the change to strange matter isn't some accident waiting to happen. It's a natural cycle. Something that happens again and again, built into space and time. You think of a forest fire, to us, that's destruction. But for the forest itself, it's renewal. It burns away the old growth. It releases what's stored in the ground, and it makes room for new life to start. So maybe strange matter works like that, but for a galaxy, a kind of cosmic pruning. Imagine a part of space that's grown old. All its stars have burned out. The galaxies there are dark, just filled with what's left over: white dwarfs, neutron stars, black holes. It's a graveyard. Everything useful has been spent. And in that state, where nothing's happening, maybe the conditions finally become right. A neutron star collision, or the slow fading of a magnetic field, could trigger that first stable Stranglet. And then the conversion starts. It moves through the dead galaxy, but not as an ending, as a reset. It takes all that locked up, degenerate matter, and turns it into something new. A sea of strange quark matter, that becomes the raw material for whatever comes next. From that dense, uniform sea, through some instability or a collision, new structures might form. Some ideas suggest this strange matter could fragment into bubbles. Those bubbles could come together. They might even create the seeds for new kinds of stars, or become the cores where ordinary matter could start to gather again. So in this picture, the universe doesn't have a single story. It has seasons, long stretches where things expand and light exists, where stars shine and chemistry builds complex things. And then periods of contraction and change, where regions get recycled back into their most basic, stable form. This phase transition to strange matter becomes the universe's way of starting over. It's a driver for cosmic evolution. As natural as the first stars creating heavy elements inside them, that process scattered the ingredients for planets and life. This would be a deeper kind of alchemy, recycling the foundation of reality itself. That perspective changes everything. It shifts the story from an apocalyptic end to a kind of cosmic renewal. It means what we see as the terrifying end of our reality might just be the start of something else. Our universe of atoms and light would be just one phase. In a much longer cycle, the silence of a converted galaxy isn't a tomb, it's a cocoon. That cosmic reset idea goes to the deepest level. It says the laws themselves might not be permanent. A conversion event wouldn't just change the materials, it could rewrite the rulebook. The fundamental constants, they are the universe's fixed settings. The speed of light, gravity's strength, and electrons' charge. They seem unchangeable, but in theory they're not magic numbers, they come from something deeper. From the quantum vacuum's properties, the lowest energy state of the fields in space. Our constants are what they are because our vacuum is what it is. Now, if strange quark matter is a truer, lower vacuum state, then its dominance changes everything. The transition wouldn't just rearrange particles. It would reconfigure the fields that give those particles their properties. Inside a region of true strange matter vacuum, the constants could shift. The strong nuclear force, which dictates how quarks interact, might get stronger or weaker. The masses of the quarks themselves could change. Electromagnetism might operate differently. The new universe wouldn't just look alien, it would be alien, operating on a different set of physical axioms. The chemistry of life, star formation, the very concept of an atom. All of it depends on the precise tuning of these numbers. Change them even slightly, and the processes that built our world become impossible. This leads to a staggering thought. Imagine a conversion front sweeping through the cosmos. Not as a uniform wave, but as a process with variations. Like ice crystallizing on a window, the new vacuum state might form in patches, with slight differences in how the fields settle. The result is a cosmos fractured into domains, each domain a vast region of space, operating under its own slightly different laws. In one, the strong force is a bit stronger, making atomic nuclei unstable. In another, electromagnetism is weaker, preventing complex molecules from forming. These domains would be separated by boundaries, walls of energy where the constants transition from one set of values to another. To an observer from our universe, crossing such a boundary would be an end. Not a physical death, but a conceptual one. The rules that govern your body, your thoughts, the very particles you are made of, would cease to apply. You wouldn't just stop functioning, you would stop being possible. The new domain would be, for all intents and purposes, a separate reality. A place where the logic that allows for observation, for understanding, simply does not exist. It's the ultimate form of isolation. Not being unable to communicate across the void, but being unable to even conceive of what lies on the other side. Our mathematics and physics are a language built to describe our vacuum. They might have no translation for a domain where the constants have shifted. That region would be, to us, fundamentally incomprehensible. Not because it's complex, but because the foundational axioms of its reality are different. This transforms the strange matter idea from a story about matter into a story about knowledge itself. It asks what it means for a universe to be knowable. And it suggests the stability we rely on, the consistency of physical law, might be a local condition. A temporary agreement in our small corner of a much wilder, more varied cosmos. That idea of a fractured universe with different rules in different places leads to a question, a really unsettling one. The universe is huge and old. The ingredients for life seem common. So why don't we see anyone? That's the Fermi paradox, the silence. People have suggested all kinds of answers. Maybe life is rare. Maybe civilizations destroy themselves, or they decide not to talk. But what if the answer isn't about life or society? What if it's built into physics? The strange matter idea gives us a dark possibility. It could be the ultimate filter, a cosmic reset button, something that reliably clears the board before anyone gets too advanced. Think of a civilization reaching our level or higher. They build particle colliders, they study neutron stars, they try to understand the fundamental forces. And in doing that, they might create the exact conditions to form that first stable strangelet. Or maybe they just wake one up. A single mistake in a high-energy experiment or while mining a dead star could set it off. The conversion starts, it spreads at light speed, no warning, no way to stop it. A civilization, any civilization, could be gone in an instant, not from war or mistakes. From a phase change, their whole star system and then their whole region of the galaxy turned into a dark, dense sea of strange quark matter. From a distance, it would just look like a patch of space going dark. Stars vanishing, signals stopping, a silent, spreading shadow. A galaxy could be slowly eaten by these growing bubbles of new physics, each one a grave marker for a civilization that reached too far. It solves the paradox, efficiently and terribly. The reason we see no one is because they're all gone, not hiding, not dead by their own doing, but unmade. By a reality more fragile than they realized. Their greatest triumph, understanding physics, becomes their end. It implies a terrible trade. The urge to understand the universe might come with a final risk. That the deepest truths are protected by a trap, a filter made of physics itself, keeping the cosmos quiet. A place of simple stars and silent worlds. It means we might be in a narrow window. The time after a civilization appears, but before it runs the experiment that ends it. Our existence now isn't proof of safety. It could be a timer, a countdown. This changes how we see our place in everything. We're not just watching, we're part of a dangerous experiment. One the universe has run over and over. The great silence isn't empty, it's crowded with ghosts. The ghosts of worlds that learned physics' final lesson. That silence isn't just a lack of life. It's a question, and it echoes through every part of science. The strange matter hypothesis, it's more than a cosmic threat. It forces these different scientific worlds to collide. It creates a shared problem, one that no single field can solve on its own. For cosmologists, this isn't just about dead stars. It's about a new class of cosmic event. A phase transition in the universe's history. One that could rival the Big Bang. Imagine a universe ending not in heat or cold, but in a wave of crystallization. So they have to model that. How would such a transition move through the cosmic web? Would it leave imprints on the large-scale structure we see? Could certain voids or cold spots in the cosmic microwave background, could those be scars from ancient conversion events? It reframes cosmology, from a study of beginnings to a study of potential endings and rebirths, all governed by the same physics. Meanwhile, particle physicists are pushed to their limits. Quantum chromodynamics is hard to solve, especially in the low-energy, high-density regime of a neutron star core. The strange matter hypothesis is a direct challenge. It demands more precise calculations of the strong force, under conditions we can't replicate on Earth. They use supercomputers, lattice QCD simulations, trying to map the equation of state for matter at densities 1,000 trillion times greater than water. Is there a true, stable ground state for quark matter? The answer is in those billions of calculations. In the subtle interplay of quarks and gluons their equations describe. This speculative idea from astrophysics, it gives their theoretical work a concrete goal. A dramatic one. Even materials science gets pulled in. No lab can create the pressures inside a neutron star. But the concept of ultra-dense, degenerate matter, it inspires new ways of thinking. How do phases of matter behave when pushed beyond all everyday limits? The theoretical structures proposed for strange matter, color superconductivity, crystalline quark arrangements, they challenge our understanding of order and stability. They represent the ultimate frontier of material states. This cross-pollination is where progress happens. A cosmologist's observation of a peculiar star forces a particle physicist to refine a model, which then suggests a new signature for astronomers to hunt. It shows how a single, speculative concept can act as a catalyst. It drives entire communities to ask sharper questions, to look at their data with new eyes, to collaborate across the traditional boundaries of knowledge. The value isn't just in proving the idea right or wrong. It's in the new pathways we build while trying to find out. The next part of this story won't just come from theory. It'll come from new machines, new eyes and ears. Instruments being built now with a sensitivity we've never had before. And this search for strange matter, it's moving out of speculation into hard evidence. Statistical evidence, and that requires scale. We can't just find one or two odd neutron stars. We need hundreds of thousands of them to see the patterns. The outliers, to understand the population as it really is. That's what the Square Kilometer Array promises, the SKA. It's not one telescope, it's a network. A vast network of radio antennas spread across continents. Its total collecting area will be, as the name says, about a square kilometer. It'll be the most sensitive radio telescope ever built. And one of its main targets will be pulsars. The SKA is predicted to find more pulsars in its first full year than we've found in all of history. We're talking about mapping hundreds of thousands of these cosmic lighthouses. With a sample that immense, we can finally ask the question, do all neutron stars follow the same mass-radius rule, or are there families, distinct groups? A cluster of objects that are just too small, too dense to be made of neutrons, that would be a powerful, indirect sign of strange stars. It's like taking a census of a whole city and finding a group of people who are all 7 feet tall. They might not tell you their story, but their existence points to a different origin. The SKA will give us that census of the dead star metropolis. But to see inside these objects, we need a different sense. Not sight, but touch. We need to feel vibrations in space-time itself. That's gravitational wave astronomy. Our current detectors, LIGO and Virgo, opened this window by listening for violent mergers. Black holes, neutron stars colliding. The future is in space. Missions like LISA, the Laser Interferometer Space Antenna. Imagine 3 spacecraft, flying in a perfect triangle, millions of kilometers apart, connected by lasers. They'll form the most sensitive ruler ever made, able to detect the subtle stretching of space from a passing gravitational wave. And LISA will listen to a different part of the spectrum. Lower frequencies, that's where you might hear the continuous hum of a single spinning neutron star, or more tantalizing, the sudden glitch, the ring of a starquake. If the core of a neutron star undergoes a phase transition, if a region of neutrons suddenly melts into strange quark matter, the whole star will ring. Like a bell, it will vibrate at specific frequencies. LISA could, in theory, detect that seismic signature from a star in our galaxy. It would be a direct probe of the cataclysm happening deep inside, a snapshot of matter rewriting its own rules. These observatories, one mapping the sky with radio waves, the other feeling its ripples, they represent a holistic approach. We're building machines that don't just look at the universe. They listen to its heartbeat. They feel its tremors. The data they gather over the coming decades could transform our strangest hypotheses into confirmed facts, or finally lay them to rest. This mystery of strange matter might not be solved by one brilliant idea, but by a relentless, collaborative gathering of light and sound. From the depths of space, you have a scientist, they're standing in front of people, and they have to explain something. This idea that could, in theory, end everything. The room is quiet, and the question is, how do you talk about that? How do you talk about something that's fascinating and important and also completely terrifying? Without causing panic, without being misunderstood, that's the core problem. Communicating science where the probability is very low, but the consequence, if it happened, is very high. There's a big gap between what's theoretically possible and what's practically probable. But in people's minds, that gap can disappear. If you hear that a particle accelerator might create something called a Stranglet, your brain doesn't latch onto the might. It jumps to the consequence, the story takes over, the imagery is vivid, and all the complex physics that makes it unlikely. The nucleation barriers, the charge requirements, the evidence from cosmic rays, all of that gets lost. So there's a tension. Scientists have to be transparent. They have to talk about the speculative edges of their work, the potential implications, but they also have a responsibility. Not to stir up fear over things their own calculations show are almost impossible. It's a balance between honesty and reassurance. Think of a weather forecaster. Their models might show a catastrophic storm is possible, under certain conditions far away, but all the current data says those conditions won't come together. So what do they lead with? The storm that could happen, or the clear skies that almost certainly will? Responsible communication means leading with the clear skies, and then carefully explaining the models, the safeguards. The same principle applies here. Public trust in science depends on this. That trust goes away if people think scientists are hiding dangerous truths. But it also goes away if every far-out theory is presented like an imminent threat. It becomes the boy who cried wolf. Then people stop listening to the real, pressing issues. The goal isn't to hide the strange or scary ideas. It's to frame them accurately, within a hierarchy of risk. We live with tiny, theoretical risks every day. The ground could open into a sinkhole. A plane could fall. We know these are possible, but they're so improbable that we don't live in constant dread. The job is to help people put a cosmic hypothesis like strange matter conversion into that same mental category. A profound intellectual puzzle, a window into physics. But not a reason for sleepless nights. This task is more crucial now than ever. With complex information and fast headlines, it requires patience, clarity, a shared commitment to nuance. We should celebrate that we can even conceive of these grand, terrifying ideas, and also trust the meticulous, gradual process of testing them against reality. The real wonder isn't in the fear. It's in the fragile, collaborative project of trying to understand. A stable, negatively charged Stranglet appears in a lab. That's the seed, the trigger. According to the models, what happens next is precise, almost anticlimactic. The Stranglet, being negative, is pulled toward a positive atomic nucleus nearby. It makes contact, the conversion starts. The protons and neutrons of that nucleus dissolve, their quarks get assimilated, the Stranglet grows just a little. But here's the turn. That first conversion releases energy. It also changes the Stranglet's charge. By absorbing a positive nucleus, the Stranglet's own net charge becomes less negative. It might even flip to positive. And a positively charged Stranglet is repelled by all other atomic nuclei, like pushing the same ends of two magnets together. It can't get close enough to touch another nucleus. The runaway conversion stops, almost before it starts. The now larger speck, likely positive, behaves like any other heavy, charged particle. Gravity and electromagnetic forces act on it. It might slowly sink through the lab floor, through the rock beneath, drawn down by its immense density. On its way toward Earth's core, it would bump into atoms, but without direct contact to their nuclei, it just nudges them aside. A tiny, dense bullet passing through a fog. Eventually, it settles into the Earth's core. A microscopic alien artifact, trapped in molten iron and rock. A curiosity of unimaginable density but harmless. A geological oddity, not a threat. This step-by-step outcome is why the scientific community sees the accelerator risk as negligible. It demystifies the process. The laws that allow the interaction also contain the safeguards. The sensational version needs everything to go perfectly wrong. The grounded model shows reality with its balances, tends to correct. The nightmare isn't impossible, but it demands a perfect sequence of failures. A strangelet that forms with the exact wrong charge and maintains that dangerous charge through countless absorptions. A house of cards in a quantum hurricane. The thought experiment does its job. It replaces vague fear with a specific, physical sequence. You trace the logic from a terrifying premise to a quiet, almost mundane end. The universe, in this view, isn't on a knife's edge. It's built with a gentle slope. Guardrails we are only beginning to understand. The most valuable discoveries are often the questions, not the answers. This whole hypothesis, it's huge, cosmic in scale, but it really comes from a simple question. What is the true ground state of matter? That question came out of the equations, quantum chromodynamics, and it sent ripples through physics. It makes us build better telescopes, more sensitive detectors. It pushes theorists to solve problems in dense matter physics, problems they might otherwise ignore. The pursuit itself sharpens our tools, it refines our vision. We're not just hunting for a particle, we're mapping the boundaries of the possible. Each observation that rules out a dangerous scenario, each calculation that defines the nucleation barrier more precisely. That's a victory. It's a step toward a deeper picture, a more nuanced picture of how the universe operates. Under the most extreme duress, the strange matter idea, it acts like a philosophical probe. It asks us to confront the foundations of our reality, to consider that the stars and planets we see, they might be in a temporary state, a higher energy state. That there could be a quieter configuration, a denser, more stable configuration, waiting in the wings of cosmic history. This isn't a call to fear, it's a call to wonder. It expands our sense of what the cosmos might be capable of. The hypothesis gives us a new lens. Through it, a dark, cold patch of space that's no longer just empty. It becomes a place where a different set of physical laws might hold sway. A pulsar with an unusual glitch. That's not merely a data anomaly, it's a potential messenger, carrying news from a realm where matter has shed its atomic skin. This shift in perspective, that's the real gift of such far-out thinking. It re-enchants the universe with possibility. The value lies in the intellectual journey, in the collaborative effort, spanning astrophysics, particle theory, computational science, all to chase down a single, elegant idea. Whether strange quark stars are ever confirmed, the process of looking has already changed us. It has shown how fragile our reality might be, and how robust. All at once, it reminds us that we are participants in a grand, ongoing experiment. The cosmos is the laboratory, and our curiosity is the instrument. In the end, the hypothesis matters because it dares to sketch a universe far stranger and more dynamic than we ever imagined. And in doing so, it honors the human drive to look into the dark and ask, what else is out there? The weight of these ideas can feel immense. But when you step back, the evidence starts to form a picture. The strange matter hypothesis isn't a prophecy, it's a question, a profound question written in physics, and the universe seems to offer quiet answers. The first is the nucleation barrier. Creating that first stable seed from ordinary matter isn't just difficult. It requires a perfect convergence, a specific density, a specific temperature, a specific arrangement of quarks. And the universe is a messy place. Perfection is rare, then there's charge. For a chain reaction to start, the strangelet likely needs a negative charge to attract nuclei. But the natural dynamics in dense environments tend to produce neutral or positive configurations. The physics itself has a bias toward stability. The most compelling argument is observational. We are here, our galaxy is here, stars are shining. For billions of years, cosmic rays of unimaginable energy have bombarded dense objects. Neutron stars have collided. If catastrophic conversion were common, the chain reaction would have ignited long ago. The great silence we perceive might not be a graveyard. It might be a universe operating under resilient rules. This doesn't invalidate the hypothesis, it contextualizes it. Strange quark matter could exist. It might be the true heart of some neutron stars, but it's likely locked away, quarantined by the forces that forged it. The idea transforms from a ticking clock into a piece of an unsolved puzzle, a key to understanding bizarre states of matter under pressures we can scarcely conceive. It remains a compelling mystery at the intersection of particle physics and astronomy, not because it threatens our end, but because it challenges our understanding of matter's fundamental nature. This measured perspective is crucial. It lets us engage with the grandeur of the idea without being paralyzed. We can explore the edges of possibility using science, while trusting in the stability that has allowed life to arise. End curiosity. The hypothesis invites wonder, not dread. It opens a window onto a cosmos far stranger than we imagined, yet far more steadfast. The cosmos isn't a still museum. It's a living laboratory, running experiments on scales we can barely imagine. The strange matter hypothesis points to that. From the cores of neutron stars to the idea of cosmic conversion. It tells us reality might have a deeper floor, a quieter one. The universe of atoms and light we know could be just one phase, a chapter in a much longer story. This idea doesn't shrink our world, it expands the mystery. Every ordinary thing, every star, becomes a kind of quiet defiance, a temporary arrangement. Exquisite and fragile. Thinking about this possibility does something. It stretches the imagination, it pushes physics to ask its boldest questions, and it builds a respect for the delicate balances. The nucleation barriers, the charge symmetries, the cosmic safety catches, all the things that let our reality exist. That's the real value of the search. Not proving a doomsday, but mapping the edges of what's possible. Every telescope observation, every supercomputer calculation, it's a step toward understanding the full spectrum. We're learning the universe's vocabulary of matter, so let this be an invitation to marvel at the complexity in the silent dark, to support the slow, collaborative work of science as it pieces together the deepest secrets, and to always look deeper. The next great revelation is waiting, not in fear but in the next question, the one we're brave enough to ask.